Hi, my name is Jim, and today we're going to be discussing part 3 of parallel circuits, and this is probably the most preferable method to use, even though it's a little bit more difficult than the product over sum or the current method. And before we get into it, let's just do a little general review on this. We're working with resistance and conductance, and they both basically tell us the same circuit parameter. For example, this table here is 3 feet higher than the floor and 5 feet lower than the ceiling. No matter where you measure from, it's still going to put you exactly at the right height for the table. So resistance is the opposition to current flow, and conductance relates to how easily the current can flow, and they have a reciprocal relationship. Now, what we know about series circuits is we have R total equals the sum of each individual resistor. Now, resistors are kind of comfortable because you can buy them, you can hold them, you can look at the color bands on them, you can measure them. But conductance, well, not so much. You mathematically transform the resistance into a conductance, so you're kind of working in the math domain here. So if we look at a parallel circuit with resistors, what we end up with is the conductance total, and the unit here is going to be the Siemens. That's capital S as opposed to small s for seconds. It's simply going to be equal to the sum of the individual conductances through each resistor. Now you can see that the sum in the sum is mathematically pretty easy to do. Now if we take a look at the relationship here, as we have the conductance G is equal to 1 divided by the resistance, and again that's in Siemens, capital S, and the resistance is 1 divided by the conductance, and that of course is going to be in ohms. So if we take this formula here and we look at it a little bit, we can break it down into something I believe you will recognize. Using this reciprocal relationship, we could say that the total conductance is equal to 1 divided by the total resistance. And in a similar manner, the conductance of resistor A is simply 1 over the resistor A, and resistor B and resistor C. And then if I wanted to, I could wiggle this around a little bit. Don't want to spend the time on the math. But we end up with our total is equal to 1 divided by 1 over R1 plus 1 over RA plus 1 over RB plus 1 over RC. And with regard to that, we could keep going. So it's a robust way of finding the total resistance, and kind of problematic, but if you're good at a calculator, you can enter this whole thing on one line using the -1 key. That's raised to the -1 power. So that's kind of our background here, and when I flip this page is what we're going to be looking at is the conductance equivalent to capacitors and inductors. So again, opposition to current flow, ease of current flow, and everybody's seen the term Z for impedance, and its unit of measure is the ohm. X sub L is inductive reactance, unit of measure is the ohm, and X sub C is capacitive reactance, again, unit of measure is the ohm. Now, if we look at this from the ease of conducting current, we end up with a new term, and that's Y, and that's called the admittance in Siemens. And Y and Z are kind of going to be opposites to each other, and we can look at the susceptance, that's the inductive susceptance, and that has to do with how easily current can flow through an inductor, and that's going to relate to inductive reactance. And then finally we have capacitive susceptance, which relates to how easily current can flow through a capacitor, and that's going to relate with X sub C. Make a C there. That's good. So let's go down and explore this a little bit further. Z equals 1 over Y. Okay, just a reciprocal relationship, and therefore the admittance Y is equal to the reciprocal Z. Likewise, the inductive susceptance is equal to 1 over the inductive reactance, and the inductive reactance is equal to 1 over the inductive susceptance. The capacitive susceptance is equal to 1 over the capacitive reactance, and the capacitive reactance is equal to 1 over the capacitive susceptance. And I hope I got all those terms right. So, if we let XL equal 20 ohms, we would express that in polar form as 20 at plus 90 degrees ohms. Now, if we wanted to find out what the inductive susceptance was, we simply take the reciprocal of that. I'm going to be dividing that into 1 at 0 degrees, and I like to write it this way so I don't get confused with the angles. And what that'll give us is, and this is going to be in the parallel form, in the polar form and in the rectangular form, is this will give us 50 at negative 90 degrees milli Siemens. And likewise, in the rectangular form, this would be negative J, 50 millisiemens. Now, what we note here is that when we went from the inductive reactance, which basically has an angle associated with it of plus 90 degrees, we move into the conductance environment. What we do is we change the sign of that. Here we have a negative 90 degrees in polar form and a negative J in rectangular form. So this is probably the most confusing part about this, is the angles change signs when you go from one into the other. Likewise, for an example, if we have the capacitive reactance equal to 10 ohms in polar form, we would represent that as 10 at negative 90 degree ohms. And if we wanted to find the capacitive susceptance, we would take the reciprocal of this like we did before, and that would come out to be 100 at plus 90 degrees millisiemens, or expressing that in a rectangular form, this is polar form, would be plus J 100 millisiemens. So there's polar and rectangular for both of these, and it's up to us to figure out what we want to do. If it's adding and subtracting, we want to use rectangular. For multiplying and dividing, it's easier in polar form. So let's get into an actual circuit here. So we have three components in parallel: a 10 ohm resistor, a capacitor of some value and some frequency that has a negative J5 ohm reactance, and an inductor with a positive J8 ohm value. And what we can see from this, as we talked about in the current solution, is that since more current is going to flow through the capacitor in this case, the overall flavor of this circuit is going to be capacitive. So the inductive component is going to subtract from the value of the capacitive component ultimately when we get there. So let's convert each one of these three into its respective forms, and the conductance G equals 1 over R equals 1 over 10 equals 100 millisiemens, and representing that in polar form would be 100 at 0 degrees millisiemens. Likewise, the capacitive susceptance is equal to the reciprocal of the capacitive reactance, which would be 1 over negative J5, which turns out to be 200 at plus 90 degrees millisiemens. Lastly, we have the inductive susceptance is 1 over the inductive reactance, 1 over plus J8, and that comes out to be negative J 125 millisiemens. And if you need to see the math on that, it would look like this. The reciprocal of 1 over J would equal negative J. Anyhow, that in polar form is 125 at negative 90 degrees millisiemens. Now we're ready to get down to business here. So we're going to write our equation here. We want to find the total admittance, and then we want to eventually convert that into an impedance and see what we end up with. So we'll start out with the real here. The admittance is equal to 100 millisiemens plus J 200 millisiemens, which comes from this guy, minus J 125 millisiemens, which comes from this guy. And if we add them together and combine like terms, which are going to be the J terms, we end up with 100 millisiemens at plus 75 plus J, 75 millisiemens. So this would be the rectangular form for the admittance. And you notice that it only has two elements in it because the inductive component partially cancels the capacitive component. All is good. Let's convert that into polar. So business as usual. The admittance equal to square root of the resistive component, or the conductive component more correctly, 100 millisiemens squared plus 75 millisiemens squared, and the angle is going to be the inverse tangent of 100 over, or 75 over 100, and what that gives us in polar form is 125 at plus 36.9 degrees millisiemens. So we're in pretty good shape with that. Let's get it into the impedance form, which I think we'd be more comfortable with. So the impedance is equal to the reciprocal of the admittance, 1 at 0 degrees, standard business, divided by 125 at plus 36.9 degrees millisiemens. And you can't forget the milli in this. That's e to the negative 3. And that comes out, and that gives us a value of impedance of 8 at negative 36.9 degrees ohms. So that's telling us that this is a capacitive circuit. And we might suspect that because we know more current is going to flow through the capacitor than through the inductor. So that high-level sanity check makes me feel good. At least I didn't make a mistake with the angles. Now let's break this down into real and imaginary components in the impedance form. So the impedance real is going to be equal to 8 cosine of the angle, negative 36.9, and that comes out to be 6.40 ohms. And the imaginary component is 8 cosine, 8 sine, shame on me, there we go, sine of negative 36.9 degrees, which turns out to be negative J 4.80 ohms. Now, the 0 sitting on the end here simply means that that's accurate to the hundredths digit. Tens digit. Okay, so we have that, and if we elected to, now what we can do is come up with an equivalent series circuit, because we've got it right here. You know, it's kind of an artifact of calculation, and that's simply going to be a 6.40 ohm resistor in series with a capacitor with a value of negative J 4.80 ohms. So, going back into the parallel circuit for a minute, this is going to be our equivalent guy that we start with. There's our 10 ohms, and now it'd be kind of nice to know what value of C we end up with. And the reason is because part of the value of C, which is negative J5, was canceled by the J8 inductance. So if I work this through with 75 degrees millisiemens, searching for the impedance of the capacitor, comes out to be 13.3 repeat at negative 90 degrees ohms. Now, what you should make of this is that the resistive element remains the same, but in the parallel equivalent circuit, we only have a capacitor, and its value, its opposition to current flow, went up a lot, from 5 to 13.3 ohms. So in the equivalent circuit, the actual current flowing into these two parts is significantly less than what we would have flowing in this part and in this part. And remember, algebraically, they subtract from each other. So that's kind of a little bit abstract form here, but the fact is if we had these both being equal, they would completely cancel, and the impedance of the whole circuit would be 10 ohms. And what we're seeing here is a component of that in our little parallel circuit. And that would be a parallel resonant circuit, but we're not there yet. So notice that these values are very much different. The 10 ohms parallel is equivalent to 6.4 ohms series, and the 13.3 ohms parallel for the capacitor is equal to 4.8 ohms, negative J, 4.8 ohms for the series circuit. So these values are different, and these two circuits are equivalent with the condition that is at one and only one frequency. You change the frequencies and all of these calculations are different. Last step here is, let's take a look at an admittance diagram, another new term, and it's basically the same thing as what we've been doing from the beginning on series circuits here. We have plus J and minus J, and I'm going to put a dot at 100 millisiemens on the real axis to represent the conductance of the resistor, and a dot here at plus J 75 millisiemens, which is to represent the combination of the inductor and the capacitor in this form right here. That's where we get the 75 from. So if we play dot the lines here, we end up with 125 millisiemens. That's him. And the angle in here is 36.9 degrees right there. So an admittance diagram is very similar to an impedance diagram. Is the only thing you got to be very careful of is the sign of the J values. So if we come over here, we can also come up with an impedance diagram. That's kind of business as usual. No surprises here. We're coming over on the real axis to 6.4 ohms, and down on the negative J axis to 4.8 ohms. Dot the box, draw the line, and what we end up with is 8. That's a dot right there. It's hard to see. 8 ohms, and the angle is, as suspected, 36.9 degrees. Now all that's nice. Got a whole sheet full of calculations here. How do I know it's right? Well, let's prove it. And what we'll do is we'll use the current method, and what we ought to end up with is the same impedance that we got when we did the admittance method. So we're going to start first by finding out what the capacitor current is, and that would be this guy here. So that would be equal to the voltage divided by the impedance of the capacitor. And when you say impedance of a capacitor, that means magnitude and direction, whereas the term capacitor reactance infers that there's a magnitude and direction. So I'm letting V equals 10 volts at 0 degrees here. And when you do this, you usually use a normalized 1 at 0 degrees, but to stay out of fractions and decimals, I chose 10 volts at 0 degrees. That doesn't matter, because the current flow through these elements is proportional to the voltage. The three elements follow Ohm's law. So for the current flow, I get a plus J 2 amperes, and for the capacitor and for the inductor, it comes out to be 1.25 amperes flowing down here. And the signs are opposite, and really what that means is that as far as an AC signal is concerned, if the capacitor current is flowing this way, the inductive current is flowing that way, and contrary-wise. But we're not going to look at that right now. So, if we take a look at I C minus L, subtracting the inductive current from the capacitor current, simply because it's smaller, what we end up is with a current of J 0.75 amperes. So that plus J means that the current is in fact leading the voltage, and that's what we would expect in a capacitor circuit. So the current diagram on this, just looking at these two guys, is just this without a real component in it. is here's our J2 amperes and here's our negative J1.2, and we end up with a positive J0.75 amperes. So that's a partial current diagram just with the two imaginary parts. Now let's mix in the resistor here a little bit. So the current through the resistor is 10 volts divided by 10 at 0 degrees ohms, and I'm just doing the angle thing here because I want to. And that comes out to be 1 at 0 degrees amperes. So to find the I total here, we know how to do that. Polar form is just going to be the square root of the sum of the squares. There we go. Inverse tan of 0.75 amperes. That's flowing through the net imaginary component divided by the current flowing through the resistive component, which is 1 ampere. So there we see it all expanded, and what that comes out to be for the total current is 1.25 at 36.9 degrees amperes. So I like the sign on this. Plus indicates that it's a leading current from a capacitor. We would expect that again because more current's flowing through the capacitor than through the inductor. And finally, for our sanity check here is to find the impedance. I'm going to let V divided by I total and see what that gives us. So if we take 10 at 0 and divide that by our I total here, we end up with an impedance of 8 at negative 36.9 degrees ohms, which is exactly what we had before when we found the impedance by using the admittance. So this is another tool in the chest, so to speak, and there's places where using admittance and susceptance is truly elegant, meaning that you want to do it that way because it's easier. Can't give you an example right now, but I'm too far off track. So anyway, that'll cover it with regard to the third method of finding the impedance and other parameters of a parallel circuit. And thank you for watching.